So this is another video on the quantum mechanics where we will discuss about the symmetries and the conservation law. And the first symmetry we are going to discuss is the translation symmetry. So first of all, we have to understand that what exactly the relationship between the symmetry and the conservation law. So this particular connection is given by the Noether's theorem. So this is a theorem which tells us that for every symmetry there is some sort of conserved quantity related to it. Like for time translation there is a energy conservation. For translation symmetry that we are going to discuss here, there is a conservation of momentum. So the proof of the Noether's theorem is quite mathematical, but if you want to know about this and if you're curious about this, that how the symmetry is related with the conserved quantity and all that stuff, I will prefer to use the the Goldstein classical mechanics. In that particular book you can find out the derivation of this particular Noether's theorem. So the topic of this particular video is to understand the translation symmetry and to prove that if there is a translation symmetry, there is a conservation of momentum. In the quantum mechanics especially we are going to discuss about it. The conservation laws in the classical mechanics is also same, but the proof that we are going to do in the quantum mechanics is quite different. So let's see what is this particular translation symmetry. So translation symmetry, first of all we have to understand what is translation operator. So translation operator is represented by this. What this does is that it shifts your function by a distance a. It shifts your function by a distance a. Suppose that this was your function. When you apply your translation operator, the function shifts by a distance a, because this was your initial position and this was after you applied your translation operator. So this is the sign of representing the translation operator, and that is the basic meaning of the translation symmetry, that it shifts your function from a distance a. Okay, so this is a basic definition. Now let's discuss about the formula of this particular operator, that how we define this particular operator. So this particular operator is defined as e raised to the power minus I a p cap divided by h bar. So this is the formula of the translation operator, and the proof you can find not in the Griffith's book, because in Griffith's book it directly uses the result. You can find it in the Shankar's book on the pre-college mathematics. I guess this was the name, or I don't remember the name, but I will put down in the comment section. You can use that book for the derivation, that how we exactly derive the formula of the translation operator. So this is the formula of the translation operator. Now let's discuss about what is translation symmetry. Okay, this is very important, so you have to see this very carefully and listen this very carefully. The fact is that the meaning of translation symmetry is that the Hamiltonian remains unchanged. It means a system is said to be translationally invariant. System is said to be translation invariant. It means it is not changing when the Hamiltonian is not changing when we apply the translation operator to it. So if Hamiltonian remains unchanged, we can say that there is a translation symmetry. It means you apply the translation operator, but the Hamiltonian doesn't changes. It's like the previous. It means the initial Hamiltonian is the final Hamiltonian. So if it doesn't change, so we can conclude this, that there might be some sort of commutation relationship. So yes, there is a commutation relationship, that this Hamiltonian commutes with the translation operator. And you know that what is the meaning when some quantities are commute with each other. I have discussed this in the case of the momentum and the position, that in the commutation relationship between the momentum and the position is like iota h bar, but in the case of this it is 0. Why? Because Hamiltonian remains unchanged when there is a translation symmetry. You apply your translation operator, but the Hamiltonian remains unchanged, and that is the basic formulation, and we are going to discuss about this, how this leads to the momentum conservation. So here you have your Hamiltonian commutes. It means you have your initial Hamiltonian as h bar square divided by 2m d square divided by dx square plus v of x. So this was your initial Hamiltonian. Now the final Hamiltonian, let's say h dash is equals to the h bar square divided by 2m d square divided by dx square plus v of x plus a. So here, if these two Hamiltonians are equal, it means they are not changed when the translation operator is applied. It means there is a translation symmetry. We can say that the potential which was initial is equals to the v of x plus a. So this is very important result. So you can imagine that for which value of a this particular equality holds. So from this there are two things arises: continuous and discrete. So what do you mean by this? The meaning behind this is that for which value of a the initial potential is equal to the final potential. So for example, if for every value of a this equality holds, then this is said to be the continuous translation symmetry. But when only a certain value of a will make this equality hold, it means if there is only certain value of a which is equal to the initial potential energy, then this is called the discrete translation symmetry. And in fact, this continuous translation symmetry is responsible for the conservation of momentum. This discrete translation symmetry leads to something called the Bloch's theorem, which we will discuss in the next video. But in this particular video, we are going to discuss about this particular continuous symmetry. It means for every value of a, this particular equality holds. It means obviously this potential is a constant potential. This is a constant potential. And this is your discrete translation symmetry, and this is related to what called the Bloch's theorem, which we'll discuss in the next video. So our topic is the continuous translation symmetry. Okay, so our topic is the continuous translation symmetry. Continuous translation. Okay, continuous translation. So we are going to see this, how this leads to the momentum conservation. The fact is that we are going to use the result of our previous video where we have discussed about the generalized Ehrenfest theorem, and you will get to see how. So suppose that we have a continuous translation symmetry. So I have imagined a very small translation, very small and infinitely small displacement, which can be represented as delta. So delta is, you can say that, infinitely small. Okay, infinitely small. So it is equal to e to the power iota infinitely small divided by a, 1 minute, here it will be a divided by h bar. So if here, I guess 1 minute, formula is wrong here. Here it will be equal to e to the power negative iota p the infinitesimal displacement divided by h bar. Okay, so this is your infinitesimal displacement I have imagined. Now if there is a continuous translation symmetry, it means Hamiltonian commutes with this particular translation operator. Now if this is a result, then we can say that Hamiltonian commutes with this particular result, and if this is very small, if this delta infinitely small distance is very small, I can write down this particular exponential form as 1 minus iota p infinitely small displacement, which is delta divided by h bar. It means Hamiltonian and this I p delta divided by h bar. So if there is a commutation relationship between these particular quantities, we can easily conclude that there is a commutation relationship between the Hamiltonian and the momentum, and as these are zero, we can conclude that the commutation relationship between the Hamiltonian and the momentum equals to 0. And that is what this is very important. This is very important. How? Because let me remind you that d by dt of the momentum operator is equals to the negative, I guess, iota divided by h bar and the expectation value of the commutation relationship between this and this. So if you remember, this was your relationship generalized Ehrenfest theorem, expectation value of your Hamiltonian, and here it would be any of your operator. Here we have imagined P, and putting down in the generalized Ehrenfest theorem, putting P, what you will get this as 0. What is the meaning? The meaning is that the d by dt of your this particular momentum operator, the momentum expectation value is equals to 0. And this implies that this is very important, and this implies that there is a momentum conservation. There is a momentum conservation. Roughly you can say that in the classical mechanics, suppose that velocity is constant, then when you take the derivative of this particular velocity with respect to time, it came out to be 0. It means velocity is constant. Okay, just like this here, the time derivative of momentum is expectation value is constant, and this implies the conservation, momentum conservation. And that very important definition you can see in the Griffiths, that the translation symmetries implies the momentum conservation. So this is only implied by the translation symmetry. This is implied by the translation symmetry. So this was our video on the momentum conservation and the translation symmetry. So we have discussed about the continuous symmetry, continuous translation symmetry. There is another discrete continuous symmetry which is quite complex, but we'll try to discuss this, and this is related with the Bloch's theorem. You can see the reference of this particular thing in the Zetterle quantum mechanics, or moreover the one and all universal book Griffiths quantum mechanics. Okay, so this is our video where we have discussed about how the translation symmetries implies the conservation laws, like the translation symmetry implies the momentum conservation. Just like this, we will try to show this for the energy conservation and all that stuff. So this is today's video on the conservation of momentum in the quantum mechanics implies by the translation symmetry. So this is today's video. Thank you for watching my video.